Good morning to all of you. We continue with our discussion on electrostatics. In the last lecture, we had introduced concepts of electrostatic potential energy and electrostatic potential. So, let us recall, if you have a collection of charges, then there is potential energy stored in the collection of charges. So, if you have all the charges of at infinitely separated distances, and from there if you bring one charge at a time and assemble the entire charge distribution, you need to do work on the charges to assemble them, and this work that you do is actually stored in the form of potential energy of the entire charge distribution. As I mentioned before, the energy is contained in the distribution of charges. It is not present in one charge or the other, it is in the entire distribution of charges, and it does not matter in what arrangement you bring the charges and assemble the entire distribution. In whatever method you employ, finally when you assemble a charge distribution, it has a certain amount of potential energy built into the system. We then defined the potential, electrostatic potential, as the work done in bringing a unit positive charge from infinity to that point. So, if you have a positive charge, point charge at infinity, you bring it from infinity to that point where you want to calculate the potential. The amount of work you do in bringing that charge defines the potential at that point. And potential is a scalar quantity, and as I mentioned last time, it is in many problems much easier to calculate potential, and from potential, as I will tell you, electric fields can be calculated. So, as an example, what we did was last time was we calculated the potential of a point charge. Suppose you have a point charge q, the potential at any distance r from here is equal to q by 4 pi epsilon 0 r. So, that is a scalar quantity, and the potential of this point charge depends only on the distance of the point from the point charge, and the potential follows the principle of superposition. So, if you have multiple charges, then the total potential at any point is the sum of the potentials created by each and every individual charge. With this principle, we had calculated the potential of a dipole. So, if you have a minus q and a plus q charge here separated by distance 2a, then this is a dipole with a dipole moment like this. Then we calculated what is the potential at a distance r from here, and some angle theta. So, theta is the angle made between the line joining the point where you are calculating the potential and the center of the dipole and the dipole axis, and the potential at this point depends both on the position as well as the angle subtended by this line. So, then we introduced the concept of equipotential surfaces. These are surfaces where the potential, electrostatic potentials remain constant. So, these could be surfaces of arbitrary shapes. The shape depends on the kind of electric fields that you have. If you have a uniform electric field pointing in this direction, the equipotential surfaces are plane surfaces perpendicular to the electric field lines. If you have a point charge, then we saw that the electric field the equipotentials are spheres. So, if you have a point charge here q, then the equipotentials are spheres like this. These are all equipotential, this is one equipotential, this is another equipotential, they are all spheres surrounding the charge, point charge, and the spheres have center at the point charge itself. And as you know, the electric field lines are like this away from the point charge. If it is a positive charge, it is towards the point charge, if it is a negative charge. So, these are the electric field lines. So, as I have drawn here, the electric field lines are perpendicular to the equipotential surfaces. We had discussed this again last time, that if you have an equipotential surface, suppose I have some equipotential surface, say like this is an equipotential surface, then all it implies is the potential at every point on the surface is the same. I am drawing a section of that surface on this plane here. So, there is a particular curve. So, there is a particular surface over which the potential remains constant. So, that means that to move a charge from this point to this point, I do not need to do any work. In fact, I do not need to do any work in taking a unit positive charge from any point on that surface to any other point on that same surface, because they are equipotentials. The potential is the same all along the surface, which implies that there cannot be a component of the electric field which is along the equipotential surface. So, it implies that the electric field lines have to be perpendicular to the equipotential surfaces. Here it will be like this, here it will be like this. So, these are the electric field lines which are always perpendicular to the equipotentials. This we saw in the example of a sphere, that on a point charge, that the equipotentials are spheres and the electric field lines are radial lines from the point charge away. So, using this, what I want to do, which we started doing last time, is to relate equipotentials and electric fields, potential and electric fields. Now, before that, I want to show you a picture of the equipotential surfaces of a dipole and the corresponding electric field lines. Just like electric field lines, equipotentials are another way of representing the electric field distribution or potential distribution, which is helpful in understanding and in picturizing the potentials and electric field. So, what we would like to do is to relate electric fields and potentials. So, we started to do this in the last lecture. So, again let me recall, I want to relate a potential V to the electric field of the distribution. So, for this what we do is we consider two equipotential lines, equipotential surfaces, one with a potential V naught and another with a potential V naught plus dV. Two equipotential surfaces which are close to each other in potentials, one has a potential V naught, the other has V naught plus dV. Now, as I just mentioned, the electric field line will be perpendicular to the direction to the surface equipotential surface. So, this may be the direction of electric field here. Now, what I do is I move from a point A on this equipotential to another point B on the nearby equipotential. So, when I move in this direction from this equipotential to this equipotential, I need to do some work. So, work done in moving a unit charge from A to B is equal to V naught plus dV minus V naught, which is equal to dV. So, you know that potential difference is the work done in moving a unit positive charge from one point to the other. So, when I have to move a point charge from A to B, the work done is potential at B minus potential at A. So, V naught plus dV minus V naught, which is dV. So, let me call this vector as dl. So, work done is also equal to minus E dot dl. The force I need to apply is opposite to the direction of the electric field. So, the work done by the external agent is minus E dot dl, which is equal to, if this angle is theta, this is equal to minus E dl cos theta. Now, if you see here, what is E cos theta? E cos theta is the component of the electric field vector along the length direction A B. This is the dl element, electric vector points like this. So, E cos theta is the component of the electric field along the direction in which I am moving. So, this can be written as minus E L into dl, where E L is the component of the electric field along the direction of motion. So, I have an equation that minus E L dl is equal to dV. This implies E L is equal to minus del B by del L. So, E L is the elect component of the electric field along the direction of in which I am moving the charge. So, suppose for example, I consider a coordinate system here. So, let me say this is x axis, this is y axis, these are the equipotentials here. So, if I move from, suppose like let me move parallel to the x axis. So, this is V naught, some potential equipotential V naught plus dV. So, I move along the direction parallel to the x axis. So, my dl vector is actually dx vector. So, I am moving along the x axis. So, the equation which I just now wrote down, dl vector is along x axis. So, what I will get is the electric field E x will be equal to minus del B by del x. So, the partial derivative of V with respect to x is nothing but minus E x. I am writing partial derivative because the potential depends on, in general, all 3 coordinates x, y and z. In a similar fashion, if I move along the parallel to the y axis, then I can get the following equation, E y is equal to minus del B by del y, and similarly E z is equal to minus del B by del z. So, these are 3 very important relations which relate the 3 components of the electric vector with the x and y and z differentials. So, in fact, from here I can write E vector is equal to I cap E x plus j cap E y plus k cap E z, which is equal to minus of I cap del B by del x plus j cap del B by del y plus k cap del B by del z. So, if I know the potential distribution of a given charge distribution, if I know V as a function of x, y and z, I can calculate each of the 3 derivatives, partial derivatives, and hence calculate the electric field as a function of position. So, this is a very powerful method, and we started looking at an example. So, as an example, I want to look at calculation of electric field of a point charge. So, I have a point charge q here, and I know that V of r is equal to, so r is this distance, q by 4 pi epsilon 0 r. So, if I had a coordinate system here x, y, z, if this point had P had a coordinate x, y, z, then r is the distance of this point from the origin in which the point charge is sitting. So, r is equal to square root of x square plus y square plus z square. So, V of x, y, z is equal to q by 4 pi epsilon 0 square root of x square plus y square plus z square. So, now this is the potential as a function of x, y, z. So, I can calculate the 3 electric field components. So, E x is equal to minus del B by del x, which is equal to minus q by 4 pi epsilon 0 into 1 by x square plus y square plus z square raised to the power 3 by 2 with a factor of minus half into 2 x. So, you must be able to differentiate this quantity, which is 1 by r. So, 1 by 3 by 2 raised to the power of 3 by 2 of x square plus y square plus z square into minus half into 2 x, which is actually q by 4 pi epsilon 0 into I will write this as x square plus y square plus z square into x by square root of x square plus y square plus z square. So, what I have done is I have split the x square plus y square plus z square raised to 3 by 2 into x square plus y square plus z square and square root of x square plus y square plus z square. Now, what are these 2 quantities? These are nothing but, so I will get an expression for E x. So, E x is equal to q by 4 pi epsilon 0. Now, what is this? This is, as you can see here, this quantity is r square and this quantity is r. So, I get r square into x by r. So, that is the electric field component along the x axis. I will leave it to you as an exercise to show that E y will be equal to q by 4 pi epsilon 0 r square into y by r, and E z will be equal to q by 4 pi epsilon 0 r square into z by r. You look here, this equation for potential is symmetric in x, y and z. So, when you calculate differential with respect to y, all you need to do is to replace x by y and you will get the expression for E y, similarly expression for E z. So, the electric field, total electric field is nothing but I cap E x plus j cap E y plus k cap E z, which is nothing but q by 4 pi epsilon 0 r square into I cap x plus j cap y plus k cap z by r. And now we can recognize this quantity. This numerator in this numerator is nothing but r vector. X, y, z are the coordinates of this point, x, y, z is the coordinate of this point, and so r vector, this is r vector, the vector joining the point charge q to the point p is nothing but r vector. So, I get the following expression for electric field of a point charge E is equal to q by 4 pi epsilon 0 r square into r vector by r. And what is r vector by r? It is nothing but unit vector along the r direction, 4 pi epsilon 0 r square into r cap, and this is exactly the electric field that of a point charge from Coulomb's law. So, what I have shown you through this simple example, that knowing the potential of a point charge which is given by this, I can actually calculate the electric field of the point charge through this calculation. And so, this relationship which I have written here is a very useful relationship for very different charge distributions. And so, given any charge distribution, I can first calculate the potential distribution of the charge distribution. Once I know V as a function of x, y and z, I can use these three relationships to calculate E x, E y and E z, and from there the total electric field E vector. So, this was a very simple example which I wanted to show you as an example which can be used to calculate the electric field of a point charge. Now, I want to use the discussion that we are having to look at the following problem with conductors with cavities. So, let me start with a following situation. I have some conductor, arbitrarily shaped conductor. So, this is a conductor. I put an excess charge q on the conductor. So, what happens, as we have discussed earlier, that all this excess charge will sit on the surface of the conductor, because you cannot have any electric field inside the conductor because and the static situation, because if there is any charge inside the conductor, in the presence of electric field, the charge will move and it will no more be a static situation. So, finally, when you are reached a static situation, that is there are no more changes, the electric field inside the conductor must be 0. And we used Gauss's law to show that this implies that there are no charges within the conductor, no excess charges within the conductor. So, all the excess charge that you have put on the conductor is on the outer surface, on the surface of the conductor. Now, I must mention here that the charge distribution on the conductor is not uniform. For an arbitrarily shaped conductor, the charges will adjust themselves on the surface such that the electric field produced at any point within the conductor becomes 0. So, for example, the charge distribution here will be such that the electric field at this point, which is created by various charges from all points here. So, they are all in different directions. So, all this total electric field, vectorial sum of all the electric fields. So, if I take a conductor like this, and if I take a point here, this charge here is producing electric field like this charge from here is producing electric field like this, a charge from here is producing electric field like this, a charge from here is producing electric field like this charge is producing electric field like this charge is producing like this. So, I must add all the electric field contributions of all the charges present on the surface, and I should find it 0 here. So, the charges adjust themselves on the surface in such a fashion that the net electric field within the conductor at every point within the conductor is actually 0. Now, if you have a spherical conductor, by symmetry the entire charge sits uniformly distributed across the surface of the conductor. So, if you have a charge q and if the radius is r, you get a surface charge density q by 4 pi r square, because then here in this situation, because of symmetry, the charge distributes equally on the entire surface of the conductor. So, we have seen this before. Now, the question arises that suppose I have a cavity within this conductor. So, cavity within the conductor. So, I have a conductor of arbitrary shape and I have a cavity. So, this is the conductor here and I have cavity, and now I put a charge q on the conductor. So, the question is, where are these charges now sitting? Are they sitting on the outer surface only, or are they sitting on the inner surface of the conductor, or are they sitting on both the inner surface and the outer surface of the conductor? So, that is the problem we would like to see. The first thing is that let me take, as before we have done, I take a Gaussian surface which is completely lying within the conductor and encloses this cavity. So, this is the Gaussian surface, this is the Gaussian surface. Enclosing the cavity, and that Gaussian surface lies entirely within the conductor. Now, because the electric field inside the conductor is 0, the net flux crossing this Gaussian surface must be 0, because electric field at every point on the surface is 0. So, if I integrate E dot dA, then I will get 0. So, that means that this Gaussian surface must be enclosing 0 net charge. Now, as I mentioned before, 0 net charge implies that there must be either no charge within the Gaussian surface or an equal amount of positive and negative charges. Please remember, 0 net flux does not imply no charge. It is possible that there may be no charge, or there may be an equal amount of positive and negative charges. If I have equal amount of positive and negative charges within the cavity, then the net flux crossing the surface of the Gaussian surface will still be 0. So, let me assume that this particular inner cavity surface also contains some charges. So, but I must, because the net flux through the Gaussian surface is 0, there must be equal amount of positive and negative charges within the on the surface. So, let me draw some charges here. So, I have some plus charges here, and maybe there are some negative charges on some other point on the surface. So, there are positive and negative charges sitting on the in the cavity. So, now what is going to happen is, remember, there cannot be any electric field within the conductor. So, there must be electric field lines like this from the positive charge to the negative charge within the conductor cavity. These electric field lines cannot enter the conductor, because inside the conductor the electric field must be 0. Now, let me take the following path. So, I take a point charge from here, move along this line and continue to move like this inside the conductor and come back to this point. So, I start from here, go along this and take a path and come back. So, I want to calculate integral E dot dl along this path. Now, remember, we had discussed this before, electrostatic fields are conservative fields and integral E dot dl must be 0, which implies that if you have any electric field distribution, if you start from a point and come back to that same point, the net work done in taking a charge from a point P to through any circuit and coming back to the same point P, the net work done must be 0. Now, look at this path which I have taken. So, I move from here and then I move along this. Now, you see, because the electric field on at all points on this path in this region of the path is 0, this integral has no contribution from this path. Now, in this path here, there is an electric field and there is a finite length which I am travelling. So, what I will find for this path, if I call this path C, I will find that integral E dot dl along the path C is not equal to 0 in this path. Now, this is inconsistent with the fact that integral E dot dl must be 0, and so what I conclude is there can be no excess charge within the on the surface, on the inner surface. So, this inside cavity, this inner surface of the cavity cannot have any excess charge, because if it had charges, there must be equal amount of positive and negative charges, which then will result in an electric field within the cavity of the conductor. And then if I do this integral of E dot dl along a circuitous path, which partly passes through the cavity and partly passes through the conductor, I will find that integral E dot dl is not equal to 0, which is inconsistent with the fact that integral E dot dl must be 0, and hence there cannot be any excess charge within the inner cavity of the conductor. So, if I have a conductor like this, any arbitrary conductor, if I have a cavity and if I put charges q on the cavity on the conductor, all these charges must be sitting on the outer surface of the conductor. There cannot be any charge on the inner surface of the cavity. All charges are sitting excess charge, all the excess charge which I put, I am assuming positive excess charge here, all those charges are sitting on the outer surface of the cavity of the conductor, and there are no charges within the conductor cavity. So, if you touch any of these points, there is no charge at all on this inner surface of the cavity. Now, if it so happens, let us suppose the conductor is a spherical conductor and I have a cavity here, wherever I have a cavity, whatever charge if I put here, this charge will be equally distributed all across the surface of the spherical cavity, spherical conductor, and there is no charge within the surface, within the inner surface of this conductor, which is the cavity surface. There is no charge there at all. Now, I want to see what happens if I place a charge within the cavity of the conductor. So, I have now an example in which I have, so let me take for example, a spherical conductor and let me have some cavity here. So, this is my conductor and I place a charge here, say plus q. Now, I want to know what happens to the situation. Now, you see that there cannot be any electric field within the cavity within the conductor. So, what this plus q will do is to attract negative charges onto the surface. So, there will be an accumulation of negative charge on the surface of this cavity. Now, if I assume the cavity to be a spherical cavity and this point charge to be placed at the center, then you can see from symmetry that this negative charge must be equally distributed across the cavity surface. Because if you now take a Gaussian surface like this, which is lying within the conductor, the net flux must be 0 and the net charge enclosed also must be 0. So, because you have put a plus q charge here, there must be a minus q charge of accumulated charge on the inner surface of the conductor. Now, these charges obviously are coming from the conductor and hence they will leave an equal amount of positive charge on the outer surface of the conductor. And if the conductor is a spherical conductor, that positive charge will get equally distributed all across the surface of the conductor. So, what I am now seeing is if I did not have a charge within the cavity of the conductor, all the excess charge that you put on the conductor are all sitting on the outer surface without the cavity. If you have a cavity and if you put a charge within the cavity, then this charge will attract, if this charge is positive, it will attract an equal amount of negative charge onto the inner surface of the cavity, such that this Gaussian surface encloses 0 net charge. So, if you have a plus q charge here, there will be a minus q charge accumulated on the inner surface of this cavity, and so that the net flux will be 0 on this Gaussian surface, the net charge enclosed by this Gaussian surface is 0. And these negative charges will leave an equal amount of positive charge on the outer surface of the conductor, and if this conductor is a spherical conductor, then this positive charge will be equally distributed on the outer surface. And so, these two charges together are not producing any electric field outside the conductor outside, because the sum of these two electric fields must be 0 everywhere. So, from outside, for the outside point, it looks as if there are positive charges on a spherical conductor, and we know that the electric field here, because of this positive charge on a spherical conductor, is exactly the same as if the entire charge was concentrated at the center of the spherical conductor. So, look here that there is no information as to the existence of this cavity or the existence of the charge. All that you see from outside is a conductor with equally charged distribution all across the surface of the conductor. Now, think what will happen if I move this charge from the center to a side point. If I move it here, what will happen to the electric field, what will happen to the charge distribution on the inner surface, what will happen to the charge distribution on the outer surface, what will be the outside electric field distribution. So, I leave this problem to you. Please give some thoughts to find out what will happen. So, I want to leave a problem here for you. So, assume a spherical conductor of radius r 0 and a spherical cavity of conductor r s, and assume that I put a charge minus q here. So, consider a spherical conductor with a spherical cavity centered in the conductor. So, this sphere and these two spheres are concentric. So, their centers meet and a charge minus q is placed at the center of the cavity. So, calculate the surface charge density on the inner and outer surfaces, and B, calculate the electric field everywhere. So, from the discussion that we have had, so this is the conductor here and of an the radius is r 0 here, and the spherical cavity has a radius r s. Both the spheres have the same center, and at the center of the cavity I have placed a charge minus q. So, I want you to calculate the surface charge density on the inner surface and outer surface of the conductors and calculate the electric field at every point in this problem. Now, I want to take this discussion a little forward and look at the following problem. So, let me assume that I have a pair of spherical conductors. So, one conductor like this and another smaller conductor and joined by a conducting wire. So, this is a conducting wire. So, this is radius A, this is radius B, both are conductors, and this is conducting and this is again radius B. Now, what I am going to do is I throw some excess charge on this system, I throw a charge on the system. So, the charge will, because these are conductors joined by another conductor here, the charge will distribute itself, and let me assume the charge on this conductor is q A and the charge on this conductor is q B. Please remember the two spherical conductors are two different spherical conductors of different radii, and the charge will distribute in such a fashion that you have some charge q A on the sphere of radius A and a charge q B on the sphere of radius B. Now, we have discussed before that conductors form an equipotentials. So, the potential at both the sphere and the wire must all be the same, because if there was a potential difference, then that will lead to an electric field, and that electric field will ensure the charges then move and until the potential becomes equal all along the conductor. So, this conductor as well as this conductor will have the same potential. Now, I want to approximate, we have calculated the potential of a spherical conductor, and so the if with a charge q A, so potential on the surface of this conductor V A is q A by 4 pi epsilon 0 into R A. Remember the potential of a spherical charge distribution. So, if I have a sphere and if I have a charge q on this conducting sphere, And so, as far as outside region is concerned, this sphere, charged sphere acts like a point charge at this point. So, the potential at any point r from here is q by 4 pi epsilon 0 r, and on the surface at r is equal to r, which is the surface of the conductor, potential at r is equal to q by 4 pi epsilon 0 r. So, the potential on the surface of the conductor is equal to the charge carried by the conductor divided by 4 pi epsilon 0 times radius of the conductor. So, that is the equation which I am using here. So, what I am saying is, as an approximation, I am assuming that the potential of this spherical charge and this spherical conductor are the same in approximately equal to V A is equal to Q A by 4 pi epsilon 0 R A, A, the radius of the sphere, and V B is equal to the charge on that conductor divided by 4 pi epsilon 0 into B. B is the radius of that conductor, A is the radius of this conductor, and I know that V A is equal to V B, because both conductors are at the same potential. This implies that Q A by A is equal to Q B by B. Okay. So, now suppose sigma A and sigma B are the charge densities. So, if this surface charge densities sigma A and sigma B. So, here it is sigma A and here it is sigma B, then Q A must be equal to sigma A into 4 pi A square, and Q B must be equal to sigma B into 4 pi B square. So, I had this equation, I had this relationship Q A by A is equal to Q B by B, which means that sigma A into 4 pi A square by A is equal to sigma B into 4 pi B square by B. So, I get sigma A into A is equal to sigma B into B. So, I also know the electric field at the surface of these conductors. If you have a surface charge density sigma, electric field is equal to sigma by epsilon 0. So, for a surface charge density sigma, the electric field is sigma by epsilon 0. So, what I get is electric field on the surface of this conductor radius A is sigma A by epsilon 0, and electric field on the surface of the conductor B is sigma B by epsilon 0. So, and I have this relation sigma A is equal to sigma B B. So, it implies that E A times A is equal to E B times B. So, E B by E A is equal to A by B. So, the two electric fields are related to this. So, let me redraw the figure here. You have one sphere of radius A connected to another sphere of radius B. So, all it implies is the electric field at this point on the surface of this is E A, and the electric field here is E B. So, the ratio of these two electric fields is, so E B by E A is A by B. So, you see that a smaller sphere, which means if B is less than A, E B is much bigger than E A. So, the smaller the sphere, the stronger the electric field. So, what happens is, if you have two spheres joined like this, the two spheres form an equipotential, and the electric field just surrounding the smaller sphere will be much higher than that surrounding the larger sphere. So, actually I can generalize this and to say that if you have a conductor which is not spherical, but which has some sharp edges like this, then the charges will distribute in such a fashion that this is a smaller radius here compared to this radius here. So, here the sigma will be suppose I call this sigma 1 here and sigma 2 here. the sigma 2 will be much bigger than sigma 1, and so the electric field at this point will be much stronger. So, in fact, I can draw electric field lines like this. So, suppose I have a conductor like this, and if I put positive charges, so there will be some positive charges and there will be more positive charge accumulated here. So, the positive charge density will increase. So, the electric field lines here, there will be some electric field lines like this, the electric field lines will be much stronger here, they are closer to electric field lines than here. So, the electric field lines will crowd around the corner point of the conductor. So, this is a very important aspect. In a spherical conductor, there are all the points have the same radii of curvature. So, the charge is distributed equally along the surface of the conductor, but here if you have sharp edges on the conductor, then you have extremely large charge densities generated there, and as we have seen before, this electric field at this point, if it exceeds the breakdown of air, then you will have a spark created at that point. In fact, this is a very interesting concept, and this concept is used in where you must have seen lightning rods that are used to pick up the lightning. So, you have sharp edges, a conductor with a sharp edge on the top of the resonance, and this conductor is joined by a conducting wire to the ground. So, when you have clouds with charged clouds which are on top of this region here, then the very strong electric field is generated between the cloud and the ground, and the electric field lines crowd towards the tip of the conductor here, and so the charge which gets discharged from the clouds comes and goes through this conductor to the ground, and thus protects the other instruments or houses from getting shock. So, this is a very interesting application of this fact that electric field lines crowd along the corner of around sharp edges. In fact, sharp edges have to be avoided if you want to avoid any strong electric fields in your problem. Okay, so now having seen that conductors are equipotential surfaces, charges put on conductors reside on the outer surface of the conductor. Now I would like to bring in another concept, which is the concept of capacitors and capacitance. If you have any two conductors carrying equal and opposite charges, so what I do is I have two conductors, I move some electrons from one conductor to the other conductor. So, I will leave some positive charge. So, I move some electrons from this conductor to this conductor. So, I will leave a positive net positive charge on this conductor will have negative charge. So, I have two conductors which are oppositely charged and kept. This particular configuration forms what is called as a capacitor. So, you can see electric field lines will be generated between these. Because of these charges, the electric field lines will be generated, and so this particular configuration forms what is called as a capacitor. So, if you have two conductors which have one conductor has a positive charge and the other conductor has an equal negative charge, this pair of conductors forms what is called as a capacitor, and these capacitors are usually drawn by a symbol like this. This is essentially the conductor which we will discuss, which in terms of parallel plate capacitor. So, let us look at the simplest of these capacitors, which is the parallel plate capacitor. So, I have here I have two conductors. So, this is actually two plates like this, there are one plate here, another plate here, and separated by a distance d. Let me put positive charge on one and an equal negative charge on the other. So, this process of putting charges on these conductors is called charging of the conductors. charging of the capacitance. So, if I connect these two pairs of conductors to a battery, I will be able to transfer electrons from one conductor to the other conductor, and in that process I charge these two and I disconnect the battery, and what I will have is two conductors like this, two parallel plates facing each other, with one with a positive charge, the other with a negative charge. Now, this forms a what is called as a parallel plate capacitor. These are two plates which are facing each other and forming what is called as a capacitor. So, capacitor is a device where you can store charges and you can store energy. We will calculate that this particular configuration stores energy in the form of electrostatic energy, and which can be used later on for many applications. Now, as we have been discussing, these two conductors form equipotential surfaces. So, the negative charge here, the positive charge on this surface here attracts the negative charge, and these two, the inner surfaces of these two conductors get charged with positive charge here and negative charge here. So, let me assume the surface charge densities of sigma and minus sigma. So, we have discussed this problem before, that if you have charge density sigma, then it creates an electric field. So, electric field produced by this surface charge density in this direction here is sigma by 2 epsilon 0 in everywhere on this side, and it is on this side is sigma by 2 epsilon 0. This negative charge distribution creates sigma by 2 epsilon 0 here, and here it creates sigma by 2 epsilon 0 here. So, we have discussed this problem before, and we have shown that between the two surfaces of these conductors we have a net electric field given by. So, I have this conductor here, another conductor here. So, I am assuming in this calculation that these plates are much bigger compared to the spacing. The area of the plates is large, very large compared to the size of the plates is very large compared to the distance separating them. So, I have positive charges here and I have negative charges on this side, and I have an electric field in between which is equal to sigma by epsilon 0, and the electric field lines are coming like this. If the plates are very large in size, the linear dimension of the plate is large compared to the separation, then I can neglect what are called as end effects. That means, towards the ends of these conductors, the charges will not be uniformly distributed because of end effects, but I am neglecting the end effects, and I know that towards the center of the parallel plate system I will have uniform electric field. Now, I want to calculate the relationship between the charges which are contained in these two plates and the potential difference between these two. So, what is the potential difference between these two? So, potential difference V is equal to the work done in moving a charge from one plate to the other, and that must be electric field times the distance, which is equal to sigma d by epsilon 0. Sigma by epsilon 0 is the electric field, d is the distance between the two conductors. So, to move a distance d, so these electric field lines are vertical lines here. So, to move a charge from one plate to the other plate, I need to do a work, the electric field times the distance separating them, and sigma d by epsilon 0, and sigma is equal to the charge on the capacitor plates divided by the area of the plates A. So, I am assuming plate area A and plate separation D. So, sigma is q by A. So, I get V is equal to q times d by epsilon 0 A. So, what we see is the potential difference between these two conductors is proportional to the charge carried by the conductors. Now, this is for this parallel plate I have shown you, but one can show that in general if you have two conductors which have plus q and minus q charges, then the potential difference between these two conductors is proportional to the charge carried by the conductors. So, we can define a quantity here, this is a constant here which we define, and we define what is called as the capacitance C. So, we had this equation V is equal to Q into d by epsilon 0 A. So, we define C is equal to epsilon 0 A by d. So, V is equal to Q by C. So, that is a relationship. So, this 1 by C is the proportionality constant which relates V and Q, and this is called the capacitance. So, as I mentioned, capacitance is a quantity which relates the potential difference between two conductors which are carrying a charge q. So, and although I have derived this relationship for a parallel plate system, this relationship is true in general. That means, if you have two arbitrarily shaped conductors carrying a charge q plus q and minus q, they will develop a potential difference V, and the potential difference V between these two conductors will be proportional to the charge carried by the conductors, and that proportionality constant is actually the capacitance of the conductor. So, we have V is equal to Q by C, or Q is equal to C times V, and this capacitance is a quantity which is a geometrical quantity. It only depends on the geometrical parameters such as the area of the conductors, the distance between the conductors, etc. It is not dependent on the charges or potential that you are calculating. So, C is a proportionality constant. Now, in this we have calculated C as epsilon 0 A by d, that is an approximate relationship for a parallel plate capacitor, because we have effectively in this calculation neglected the effects of ends, but this is a reasonably good approximation. If you were to calculate more precisely, you will get a slightly different value of C compared to this number, but otherwise this relationship will be still valid. V is equal to Q by C, where C is the capacitance of this conductor pair. So, let me calculate, let me take an example. So, let me take two plates. Let me assume the separation is 1 millimeter. So, d is equal to 1 millimeter, and let me assume an area of 10 centimeter square. So, capacitance of this epsilon 0 A by d, which is equal to 8.85 10 to the minus 12 into 10 centimeter square is 10 to the minus 4 meter square, divided by 10 to the minus 3 meters, which is equal to 8.85 picofarad, which is actually 8.85 into 10 to the minus 12 farad. So, farad is a unit of capacitance. This is named after Michael Faraday, and it is given by if you take in volts, if you look at this equation here, if you take V in volts and Q in coulombs, C comes out to be a unit called farads. And so, this amount of capacitance of this parallel plate capacitor with two plates separated by 1 millimeter separation and each having an area of 10 centimeter square is 8.85 picofarads. So, farad is a unit of capacitance, and this particular farad is a very large quantity. So, as you can see here, this surface parallel plate capacitor has a capacitance of 8.85 picofarads. So, suppose I were to take this parallel plate capacitor, and so I take the same parallel plate capacitor, and if I so the capacitance is 8.85 10 to the minus 12 farads, and if I apply a potential difference, V is equal to 1 volt, then the corresponding charge will be C times V, which is equal to 8.85 into 10 to the minus 12 farads into 1 volt, which is equal to 8.85 10 to the minus 12 coulombs, which is equal to 8.85 picocoulombs. So, that is the charge carried by the conductors. So, what we will do is today we will stop at this point, and in the next lecture we will calculate capacitance of other configurations like cylindrical capacitors and spherical capacitors, and we will see in every case that the potential difference and the charge carried by the capacitance are related to each other, and the proportionality constant gives me the capacitance of the pair. And capacitance are very important components in electronic circuits, and we will understand a little bit more about capacitance later in later lectures. Thank you very much.